avoid work, and that's to think about geometric. So think about geometric series. Anytime that something's geometric, let's like maybe avoid having to actually take derivatives and do this Taylor expansion, okay? Even though this method will always work. Take derivatives, evaluate them at the center, divide by n factorial, right? It's just cumbersome. So today we'd like to talk about ways of getting around that. Just recall from yesterday the following two results. These two ideas. We've got centered at 0 and centered at a. It's easy to forget that. And we talked about these guys with wigs, and that was exciting. And of course we talked about the fact that Cn, this is the big thing to recall, the coefficient on the nth order term is, someone say it, the nth derivative of f evaluated at a, or 0 if we're up here, all over n factorial. Like, so if anything, actually, that was the big takeaway from yesterday. Okay? And that was like the big takeaway from yesterday. And we talked about not just that, but where it came from. We actually kind of derived that from first principles, from the most general power series. We just said, hey, what happens if you take derivatives? Like, I wonder. And again, even a bigger takeaway is that, like, isn't it incredible that we can take any function, even if it's not a polynomial, and represent it as a polynomial? That means a lot for us, right? So let's do some more power series. I'm still kind of in the same section, but at any time I can do it, I'd like to kind of hack old methods. Before we go into that though, let's do a sin x centered at pi over 3, just because it's a little more interesting than the series we gave you yesterday. Okay, so I think we wrote this up yesterday, but we'll write it again just for reference. F of x is sine, so just feel free to race ahead of me if you want. This is going to take me a second. F prime is cosine. F double prime is negative sine. F triple prime is negative cosine. Fourth derivative is sine again, etc. Okay, and then now though, this is the part that's a little weird. Now we have to evaluate all these at the center, which is now pi over 3. So just we'll take a trig knowledge here. Not too much trig knowledge. Okay, I'm ready. Sine of pi over 3 is moment of truth. Very good. And cosine? Good job, trigonometers of America. So I think these are all good. Now, so notice that like that nice, we really like centering sine at 0, don't we? Yeah. Or at anywhere else where sine is 0 would be fine too. If we centered it at pi, we get some nice results. If we centered it at 2 pi, we get some nice results too. But centering it here, notice that the power series we get will not be like the powers, we're going to have all the other powers too. The nice thing about centering at 0 is that all the even powers dropped out. Do you remember that? That was cool. That's not going to happen here, just so if that's not already obvious, because we didn't get 0 on all these. So, all right, so let's keep going. And then these just repeat, right? Root 3 over 2, etc., etc., etc. for all these. So I think that we've just done the hard work, right? So let's write out the power series centered at x equals pi over 3, just like the warm-up. Now we're at the position we were at the warm-up. I've just given you a whole bunch of derivatives at the center, and I think we're good to go. Yeah.
Is there like a general rule about how far you should go, how many terms you should write out?
Just enough to establish like a pattern. Now, a lot of times they'll be really explicit. If someone cares enough, they'll tell you like in the warm-up, please give the fifth order along or something.
If not, like if it asks for the power series,
or
if you're doing it this way, you just do it until it repeats it.
Yeah, this is pretty ambiguous instructions to write. But in the homework, a lot of times, or on our tests or something like that, we'll ask write out the power series, the first 4 terms, the first 4 non-zero terms, or something like that. And also the general term, sometimes we'll say. In which case we want actually the rule for the term. Yeah. Yeah, so maybe we can do that here. I don't know if that'll be possible. It's not always easy to do that though, right? So sometimes we won't ask for that if it's like intractable. So we'll just ask, like, well, don't try to do that because it's hard.
Okay.
We'll just say, like, write out the first 4 terms, and we'll call it good. Something like that. Okay. So it depends on the series. It's not an easy thing to come up with that. Sometimes it's really hard to come up with the rule. So, all right. So I think we're ready to do this. F of x, here's the power series. Instead of sine x, we could write root 3 over 2 plus what? Who's got it? Someone want to like volunteer? Just read this off. Go ahead.
1/2 x.
Close.
Oh, is it over?
No, not yet. Maybe you're about to say.
Oh, 1/2 x minus power 3.
Yeah. Like I said, it's easy to forget that because like you did all this hard work and you forgot that like we're still centered at pi over 3. There's a lot of people will do that.
Root 3 4. No, minus.
Yeah, root 3 over 4. Yeah. I mean, is it okay to simplify that right away? It'll be root 3 over 2 over 2 factorial. So yeah, root 3 over 4. I kind of like that. 5 over 3 to the second. Okay. Yeah. Keep going. Yeah, 1 over 12. I like that. Minus 1 over 12 because it'll be negative 1/2. Wait. Let me think for a second. Over negative 1/2 over 3 factorial. I think I'm with you. Okay. Keep going. Minus times 5 over 3. The third. Since we have one more term. Because, let me think about that too. Because it's root 3 over 2 divided by 4 factorial, which is 24. Got it. Okay. Times. Okay. And then maybe we should challenge ourselves to write the general term here. Can we do it? In terms of n? Or maybe we can't. I don't know. Maybe the answer is no. I mean, you know, one thing you could do is break it up like into 2 pieces. Like say for odd terms it's this, and for even terms it's this, because that would be something you could do, and you could define it like piecewise or something, you know, for odd and even. I think I could do it without an x as the coefficient. I don't want to take the time to do that now. I didn't say to necessarily do that, so we'll just leave it at that. But I do think that I could come up with a term if I really tried hard. Okay. Oh, really? You want to go? Let's go back and do it. All right. No, I think we could. So maybe we'll come back to that at the end if we have some time. We have lost some time in the fire drill and everything today, so I want to make sure that.
You can probably use some sort of step function.
Yeah, my first suggestion was like breaking it into 2 pieces because obviously all of the odd terms look the same and all the even terms look very similar too. So I think I could, at the very least, I know I could do that. But I might even be able to do something trickier than that. I think I have something in mind. Construct power series for e to the x. We haven't done this yet, and it's so exciting and fun because taking derivatives of e to the x is one of my favorite things to do in life. All right, let's do it. F of x is e to the x. F prime of x is, let me need some scratch paper. Yeah, that's right, it's e to the x, okay. And F double prime is, oh that's right, e to the x. Okay, so I think we're getting the idea here. And what is, if we're centering it at 0, let's start with that. Then what is f of 0? And what's f prime of 0? And f double prime of 0? All of these are, yes? All of them are 1. That's like a remarkable thing that's happening here. Okay, so I think I'm ready to do it. E to the x, or f of x, is equal to the first term, 1, plus, yeah, 1x, plus x squared over 2, plus x cubed over 6, plus x to the 4th over etc. And this one, I think we can definitely write the general term, can't we? How about x to the n over n factorial, right? So there's the power series for e to the x. It's so beautiful and so important that That deserves to be like painted on a wall somewhere too.
Isn't it already painted on the wall?
Oh, it is perfect. Good. Okay. It's so nice. And can you just verify that this has some of the desirable properties of e to the x that we like? Like, for example, could you all please take the derivative of this just for a second?
You never noticed that?
Watch it happen. Yeah? Do you see it? What are you getting? You should get the same thing, right? Isn't that beautiful? It's beautiful. Okay. And if you integrate, you get the same thing. Yeah. You get plus a constant, but you have to think about that. If we're integrating from 0 to x, then we actually get the 1. I think it'll work for you. Okay. What else to say? Yeah, good. All right, let's do b. X equals 1. This one's maybe not quite as nice, but I didn't leave room here. What's f of 1? E. F double prime is, excuse me, f prime of 1 is e all the way down e's. Okay. So we could also write this centered somewhere other than 0. Here's a. Here's b. What would it be centered at? 1. Someone else do Michael's role here. Read it off. David, say it again. Yeah, go ahead. Sorry. E plus e times x minus 1. Yeah, so e over 2 factorial. Okay, I think we're getting an idea here.
Which makes sense when you divide out by e basically x minus 1.
Yeah, this makes sense because this looks like just e times the other series. So yeah, maybe there's just like a horizontal shift in the function. It kind of makes sense that would happen.
You just plug in x minus 1.
Yeah, and that already like kind of is getting to a point that we're going to make some more of today. So. All right, so are we having fun yet?
Yeah.
So you could write that in summation notation too if you like, but I think we're doing well. Have we done cosine yet? Maybe not. Let's do it. Why don't you do it with your friends there? And we'll come back here. We'll give you a minute to start it. It doesn't say wherever to do it. I think I'd probably prefer actually etc. if I didn't tell you so.
So if it doesn't tell you,
You could do it anyway. Why would you choose something else to zero out? Try it. Don't come after me. Try it. See what you get. You can do it wherever you like. Where would you like, Simon? Okay. Actually, it'd be kind of fun for different people to do it in different places and just look at the results. Yeah, it's e to the x minus 1, but then times e. Isn't that the same thing as e to the x? So what David was saying is like, take this series. Can you get the expansion for e to the x minus 1? And the answer is yeah, sure. E to the x minus 1 is just this series with x minus 1 plugged in everywhere. Right? But that's not e to the x though, that's e to the x minus 1. One way you can fix that though is by multiplying everything by e. And that gives you e to the x again, doesn't it? So, how are we doing cosine? Check with your neighbor if they got the same thing, then like, life should be peachy, hopefully. And we'll just like write out the answer when you guys are ready. I won't show the work up here. I'll just write cosine x equals, and then we'll fill in the blank in a second. And compare this, please, with your result with sine, right, from your notes from yesterday. Maybe there should be something even happening. Okay, first term, what'd you get? Second term, what'd you get? Yeah, minus x squared over 2. Next non-zero term. Yeah.
Okay, plus the now plus factorial.
Yeah, absolutely.
Oh, I'm not even looking for the plus factorial.
You can do whichever you like. I'm emphasizing right now just the form of what this looks like because I think it's lost if you evaluate them. It doesn't matter on this first one really. What's the next term? The next non-zero term? Plus, yeah, what is it? X to the 4th over 4 factorial is what you should be getting. Minus x to the 6th over, so this is what you should be getting. Okay. Yeah, and we should check the properties of sine and cosine too. I think it would be fun to like take some derivatives of these and see that we get the right thing too. Do we get that? If we take the derivative of this, do we get a series for negative sine? You know, hopefully that stuff relates. That would be a nice way of getting this. In fact, to start with, you could, instead of doing what you just did just now on your paper, which is to take a couple derivatives, you start with sine x this series, take the derivative of that, and be done, right? So with that in mind, what about a power series for cosine of 2x?
Is this series like factored like when you punch sine x and you factor x, is this like a function of actually?
Actually, I think your calculator uses kind of some slightly different technique. I'm trying to maybe it's a very small value.
Because like that's pushing too fast for people known as a regular new comprehension.
Yeah, it's actually a little more complicated than this, but yeah. But yeah, you could do a series expansion around a particular point if you want to really find values of sine. It turns out to be like computationally intensive though to do that. So a lot of times a calculator has like a set of tables in it, really finely grained tables that it just has, and it's easier for it to store those values than anyway. And then maybe even just linearly interpolates into between or something. Okay, so one way to do this power series cosine of 2x would be to take derivatives again, chain rule, a bunch of 2's would pop out, everything would be really great. And it would work. But we're mathematicians and we'd like to use previous results as often as possible. AKA, we'd like to be as lazy as possible, right? And I have a series on my last slide for cosine x. So I suggest, what do I suggest? What does cosine of 2x mean? Well, the cosine of whatever is 1 minus that whatever squared over 2 plus that whatever to the 4th over 4 factorial minus etc., right? So what is our whatever here? Yeah, I think I can do it. Here we go. 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial, etc. But let's actually say what that looks like then. That's 1 minus 2 to the 2nd over 2 factorial, x to the 2nd, plus 2 to the 4th over 4 factorial, x to the 4th. I just want to emphasize what is the coefficient on these. Minus 2 to the 6th over 6 factorial. And if you do it by hand from scratch, you will get the same result. And I think it's not too hard to write the actual general term here. Well, maybe it is a little hard here. Let's see if we can give ourselves some space. If we index with n equals 0 here, let's see if we can write it out. It'll be, it looks like n factorial on the bottom. Wait, maybe not. How about 2n factorial on the bottom? And 2 to the 2n on top, except maybe it's a negative 2 to the 2n times x to the 2n. I don't actually know whether that's right or not. Let me look at it for a second here.
No, because then it always be positive.
Yeah, right. Negative 1 to the n, negative 2.
Oh yeah. Okay, so what do I want instead? I think I still need a negative 1 out there. I mean, one way to do it would just be to throw the negative 1 out there too, right? You could do 2n, and then let's just do negative 1 to the n out front. Does that work? You could incorporate those together somehow. Anyway. How do you get x cosine x on the way out? What are you going to do there? Take your cosine series and just multiply every term by x and walk away, right? And just verify that, like, if you did this by hand, it'd be terrible.
So let's talk
A lot of
about
rules everywhere.
Mr. Coleman, Mr. Wright, and Mr. Cooper will be in
So,
33 today at lunch.
There are a bunch of power series that are in your book, and you're allowed to use any of these now, okay?
Calling, please send report to the main office.
Page 491 in your book has a whole bunch of series that you can use without any reason. You just like know those series if you like. I don't know anything about that. It just came to the name. I gave it to you.
The very first problem, everything got really nasty. So what I did was, it was like root x squared plus 1. So what I did was, I made another function that was root x plus 1, and then just composed x
They
squared.
suggest that in the courses somewhere.
No, I didn't. I just decided I have to do that.
Yeah, it's very nice to
You can do that with any function.
I mean, some functions end up just being nasty, but as often as possible, we can find like shortcuts to avoiding like terrible algebra. Yeah,
I did the first two, and then I was like, you know what? I don't want to.
yeah, I do want you to know how to do it. I'm glad you had the experience once, but like, you know,
No,
as
I
often
did
as
the composition
possible.
thing.
That's awesome. That's very slick. If you, yeah, and now I have become expecting that you're good at doing, you know, x cosine x, we should be able to call it series.
Are there any other important ones that we should memorize?
There are a bunch on page 491 that are useful to you, and we'll derive a couple of them in class. There's none of them that you have to memorize. Okay? All of them you can rederive on the fly if you want. So, but, yeah, see, yeah, you leave them here. Okay. Yeah, I guess that's okay. Did you write in it yet?
I did not do anything.
Okay. Well, here, why don't you just come get them at the end of the day? I'll just put them back where they normally go. But... Okay. We go quick, and there's a fire drill. Shame on that first time fire drill.
This lesson kind of cleared things up, but how would you